So let's begin. Welcome, Carsten Schneider from Linz. He will talk about algorithms, ring theory, and symbolic summation.
So thanks a lot for your kind invitation. It's nice to be here. It's the first time that I'm in New York. And luckily, yesterday in the afternoon, the weather was not too bad, so I could see a bit of New York. So when I arrived, I saw the Empire State Building in the fog, and it was hard to see anything. But yesterday it was great, and today it's even better.
Are you going to run on Sunday?
Yeah, no, I have to leave after my talk, but maybe from the plane I can see a bit more. Okay, so my research topic is computer algebra, and in particular symbolic summation. But I'm always fascinated by the theory behind to justify why the algorithms work, and also to discover what are the properties that the algorithm actually deliver, and this provides me the theory. However, I'm also interested in applications. In particular, I have a big cooperation with particle physics guys, so we do heavy calculations for Feynman integrals, three-loop massive Feynman diagrams, and all these algorithms and also this difference string theory behind is used in the setting. So my talk is basically based on three parts. The first part, basically here I want to show you a bit the algorithms in action, so more the computer algebra aspect. The biggest part of my talk will be the difference ring theory, where you see how I can represent the objects and how I do the translation from the real world into the computer algebra world. And in the end, if there's time left, I would like to show you some examples from this Feynman integral calculations. Okay, let's start with a warm-up example. It's a double infinite sum, so I sum j and k from 0 to infinity. And the summand itself, you see here the factorials, j factorial, k factorial, and different linear inputs of factorials. And you see in addition here the s sub 1 and s sub 1 of n just denotes the nth harmonic number. So maybe you're more familiar to that notation, but in particle physics they prefer this notation because you can nicer generalize afterwards with these letters 1. So I prefer just in the beginning to use this notation. So if you see such a sum, you see it's rather complicated, and the parameter n is there on which this is a free parameter, and j and k are the summation variables, is completely coupled. It's very hard to see any properties from the sum. And the main goal is to simplify it. So how can we do it? Well, at least in symbolic summation, if you see such a sum, you start with the inner sum, and I basically try telescoping. This is the standard tool in symbolic summation. So let's denote the summand by fj, where I suppress the dependence on n and another summation variable k. It's just in the innermost summation variable. Given the summand, I want to find an expression g such that this telescoping equation holds. My summation package sigma that I developed the last 20 years finds that expression. So you see it's again an expression in terms of factorials times a linear combination of the harmonic numbers, the chase harmonic numbers, the k plus chase harmonic numbers, and so on. By the way, you can plug in this solution into the equation, and by simple polynomial arithmetic you can verify correctness on that level. So we have a proof certificate that this is indeed correct. Well, what have we gained? Now we sum this equation over j from 0, not to infinity in the first step, but to a truncated version. Well, on the left-hand side we get basically our sum, the truncated version, and on the right-hand side all terms vanish except at the upper bound and the lower bound by the telescoping trick. So what you see is nothing else than the discrete version of indefinite integration. Okay? We plug in our concrete expression g that I calculated, and finally I send a to infinity. And basically, using the fact that the case harmonic numbers behave like the log in the asymptotics, one can see that the expressions which depend on a actually vanish. The denominator dominates the numerator, and in the end we get that simplification. So the inner sum can be written again in terms of harmonic numbers, but much simpler. Next, I apply, well, one can do this with my package. So you load in the summation package sigma, then you insert the sum, and then there's a comment sigma reduce applied to the sum, and then you get exactly that output. And finally, you calculate the limit. And here we have, I should mention, there are special function algorithms also behind to calculate asymptotic expansions. So this limit is completely justified, and it's under our control that it's correct. It's not mathematical or something, the limit. It's our own limit where we know what we are doing. Okay, so we have this simplification. Next, we consider the next summation quantifier, and please, there's a little subtle point. The output of our sum has a pole at k equals 0. So for this simplification, I can only start for k equals 1 on, and k equals 0 has to be treated separately. And this very often happens for Feynman integrals or sums which come from that at the borders you have poles, and it's very subtle to deal with them. Okay, so let's try to simplify the next sum. Let's denote again the summand by fk, where k is the next summation variable, and we try to find a gain in expression g. But this time there's no solution. So there might be no options in indefinite summation to improve, and I have tools. Actually, I would find a solution in a different version, but let's try differently. What we also can do is that I haven't used so far the free parameter n. It was just hidden. So let's sneak it in. The expression actually also depends on n. And now I don't look for the solution of the telescoping equation, but I take the summand and shift it in n. So I have now the summand, and the summand shifted in n. And I say, well, maybe I find a telescoping solution if I sneak in parameters c0 and c1, which are free of the summation variable, and if I find a good linear combination, then it telescopes. So the chances are increased that I find something. Okay? And in this particular instance, I find the constant c0 equals minus n, and c1 equals n plus 2, and I find that expression. And by the way, you can plug in this solution into our equation, and you can again verify correctness. Again, this is a proof certificate that it's correct, and you don't have to know how the algorithm works, you just verify on this level. This is the reason why special function guys and combinatorics guys like this machinery. They don't have to deal with the algorithms, they only need that. And then they can publish because this is a proof certificate and everything is correct.
If your algorithm, if your algorithm is an algorithm, why would you certify?
Because it's, as I said, the implementation is 200,000 of lines of code, and there might be bugs.
Okay.
And I can never, I always, if I run in Feynman integrals, I have to calculate 100,000 sums, and always I enter again a new special case that I haven't treated, or I optimized something I wanted to be faster, but then I haven't treated the special case. But on this level, you are safe. Humans make errors, but this is so simple that a very simple code checker, which is proved and verified, and can verify it for you, and this is safe. Okay. Now we do the same trick. We sum our equation over k from 1 to a, truncated version. So on the right-hand side, I get that. And on the left-hand side, again, by the telescoping trick, I get that. By linearity, I can split the two sums. And that's now the main point. The constants c0 and c1 are free of the summation variable. So I can pull them out. And that's basically my original sum, and that's a shifted sum. So I have gained a linear recurrence. And by the way, if I fail to find a linear combination of these two guys, I shift another time in n. So then I might get a recurrence of order 2, and I have to shift a third time. Then I obtain a linear recurrence of order 3, and so on. So the more I shift, the more I increase the chances to find something. The higher the recurrence order is, but the more chances are there. Okay, I plug in my concrete values. I get that simplification of the recurrence. And finally, I send a to infinity. I can again calculate the limit. And I obtain this linear recurrence. Next, I solve the recurrence. In this case, it's easy because it would be just variation of the constants. But any first order recurrence can be solved. But here you get the following solution. This can be done also automatically. I find one particular solution, and one solution of the homogeneous version, if you set the right-hand side to 0. So the solution space is completely solved. So if you have a linear recurrence of order D, and you find D linearly independent solutions in a particular solution, you have the full solution space. Okay? So our original sum must also live in the solution space, because this also satisfies this recurrence. We have a proof certificate. So finally, I just look at one value, for instance n equals 1, and I can determine the C. In this case, C must be 0, and I obtain that closed form. So again, you can do this with sigma. You insert your sum, generate recurrence, produces you the recurrence that you have seen. Next, I perform the limit. I send a to infinity, and then I have the recurrence of the infinite version. Then I solve the recurrence. This is my homogeneous solution, and this is the particular solution. And finally, I take the first initial value, which uniquely determines me the solution, and I get that. And by the way, to get at n equals 1, that this is 1/2, this is another round of symbolic summation to get this 1/2. It's not so easy. You have to work again with the same tools. So summarizing, we obtain that simplification, and in the end, I have to treat the case k equals 0 separately, and that's the full simplification. And now you see this ugly sum here can be written in terms of the harmonic numbers and the harmonic numbers of second kind. And here we know asymptotic expansions, we can do analytic continuations, we can relate it to the gamma function, we know everything. And this is precisely what the physics guys love, to see such representations, because now they're in business. Okay, so let me show you the summation paradigms once more. And what you can do in sigma, you start with a definite sum, where the summand must be an indefinite nested sum with respect to the summation variable, like the case harmonic numbers, any hypergeometric term, but it can be also indefinite nested sums. You will see later, the class. And then you sum over k from 0 to n. This would be a definite sum, because the n arises here and arises here in a non-trivial way. Or it might be infinity, then it's a limit of a definite sum. But this is somehow equivalent. And given such a definite sum, I try to hunt for a recurrence by the creative telescoping paradigm, which originally was introduced by Doran Seiberger. He was here also last year. I have seen him in action. I looked a bit on the movies. So you have seen his liveliness style. And if you succeed in a recurrence, then we can do the following. I have a recurrence solver, which the coefficients of the recurrence might be given in terms of indefinite nested sums, and in particular the right-hand side might be given in terms of indefinite nested sums. So you have seen here one example. Well, the coefficients are just polynomials in n, but the right-hand side was given in terms of indefinite nested sums, namely the nth harmonic number. And then I have a toolbox which finds all solutions which are again expressible in terms of indefinite nested sums. I don't find all solutions. So if you give me an arbitrary recurrence, I would fail. But if the application is driven that one knows or one guesses or has a hope that there is a nice solution, sigma will find it. And if it doesn't find it, it's a proof there is a weird thing behind, and maybe elliptic function or orthogonal polynomials, Bessel function, something like this is behind, I don't know what. Okay? And if I find sufficiently many solutions, then I can combine the solutions to find an indefinite nested sum.
I have a question.
Yeah.
Well, the first part. Why did you call it a warm-up example?
Because you can show it on the slides. It fits on slides. I have other examples where the summand is one gigabyte, and I have to do summation. This is not anymore shown, presentable. But this is all digestible, and you can verify by hand. But when I saw it the first time and I had to deal it, this was 15 years ago, my package could do it in principle, but I had to do a lot of cosmetics and hand manipulation in my code that it worked. But now it works automatically very efficiently. So maybe let me show the machinery in action for a triple sum. It's slightly more complicated, so we have now 3 nested sums. And you see the summation bounds depend always on the other summation variables. It's very coupled, very complicated. So I start again. This is my main feature. So I start from the innermost sum on, And I compute now a recurrence with respect to the next summation variable. So I solve a recurrence, try to find a recurrence with respect to R, shifts in R. Then I solve the recurrence, I combine the solution, and it turns out that that sum can be written as a linear combination of hypergeometric terms. So this is precisely the book A equals B from Doron Seiberger, Herr Wilf, and Marco Petkovsik. That is technology from the 90s, but it's also available in Sigma. So in other words, the triple sum simplifies to a double sum. Now I repeat the game. I compute a recurrence with respect to the next summation variable. This is J. So I obtain a recurrence with respect to J. I solve with respect to J all indefinite nested sums, and I get that simplification. Now you see the expressions, well, it's even bigger. The output is bigger than the input, but the output is much nicer, because here you see the J pops up everywhere here. It's coupled, whereas the J here pops only outside, but not anymore inside of my sum. It's uncoupled. It's indefinite. And the nice thing is this class fits again into my input class. Namely, the summand can be represented within my sigma package, and I can now compute the recurrence with respect to n. I solve the recurrence with respect to n, combine the solutions, and in the end, I find the solution in terms of the harmonic numbers of second kind, and this -2 means that I have the alternating sign in addition in. And that's my simplification. And again, I have full control now, asymptotic expansions. I know how it behaves for large n, all the things, I know everything. So here, you load in the package sigma. The package harmonic sums is dealing with limits. We have asymptotic expansions for objects. And this is my package evaluate multisums, which combines the previous two packages. And you insert just your sum, and then you say evaluate multisums. In with respect to 1 minute, you get the closed form. And we do much more complicated things, and I have handled with several millions of such sums. So the code is quite robust, meanwhile. And all this is based on difference ring difference theory. Here, so there's Sergei Abramov, Michael Karr, one of the pioneers in difference ring field algorithms. Michael Singer is also involved in these technologies. A lot of things, and this is only parts. This is basically the tools that Sigma uses. Okay, and now I would like to switch to the second part. I would like to show you the underlying framework. Not all details, but if you have questions, maybe I can also discuss a bit on the blackboard, but I want to give you the main engine. And let's look, again, I want to do it application driven. Let's look at a simple example. Let's try to sum the case harmonic numbers. So it's even easier to handle. So how do I represent it in my computer algebra package? Well, I want to represent the object in terms of variables. I want to work with variables because then we have polynomial arithmetic, rational function arithmetic, then we have an algebra. So what I do is, first I construct a formal ring in which I represent my summation objects. More precisely, I start with the rational functions because I want to deal with 1 over a, or I have to deal with such objects, with rational functions. And in addition, I join a new variable where the variable s will model my harmonic numbers, s for sum. So basically, I have a polynomial ring in the variable s, and where the coefficients are from the rational function field qx. Okay. So this is I have now a link between the summation objects and the variables. Now I have to say, how do the variables behave? First, I define an evaluation function. They say, given me a variable, I know how it should be evaluated if I want to interpret it again as an analysis object. So let's see how we evaluate a rational function. Give me a rational function, so we have a polynomial in the numerator and a polynomial in the denominator. This is my rational function. So instance x divided by x plus 1. This would be x, this would be x plus 1. And then I just evaluated the polynomials and do the rational function arithmetic as long as there's no pole in the denominator. And if there's a pole, I'm in an unlucky case, and I choose any value, just by convenience, I choose 0. I just say it's 0 if there's a pole. Because I want to stay in the rational function field. I could also introduce a new symbol, infinity, but I prefer we stay in the rational numbers, so it's 0. So we know how to evaluate rational functions now. And now I extend this for the harmonic numbers, for the variable s. And I just say the evaluation of my variable s with respect to k are just the case harmonic numbers. So k equals 3 would be 1 plus 1 half plus 1 plus 1 half plus 1 third, 2 plus 1 third. Yeah. And then finally, if you give me an arbitrary polynomial, then I evaluate the coefficients. I've already defined how they have to be evaluated, and I substitute, instead of the variable, I substitute the evaluation of the harmonic numbers. It's just a homomorphic extension of the evaluation. And I call also this ring together with the evaluation in eval ring. So I have now attached variables, and I know if you give me an arbitrary expression, I know how to evaluate it as a sequence. Okay? And now we can, of course, if we are given the evaluation function, I can take an arbitrary element from my ring, and I can evaluate it as a sequence. Take f of 0, 1, 2, 3, 4, 5, and I get the corresponding sequence. And this is almost a ring homomorphism. Well, you see it's not really a homomorphism, because just look at tau of x and tau of 1 over x. Tau of x is 0, 1, 2, 3, 4, 5, this is fine. And tau of 1 over x, because at x equals 0, I have a pole, I put here 0. And then I have 1, 1 half, 1 third, and so on. If I multiply it out, I get by Hadamard product, it's component-wise multiplication, I get 0, 1, 1, 1, 1, 1. But unfortunately, this is not 1, 1, 1, 1, 1, which would be tau 1, which would be tau of x divided by x. And this should be equal to z if it's a ring homomorphism. So what is the trick? Well, there was a pole, but there are only finitely many poles. So let's do the trick. We say two sequences are equivalent. So this is very common in symbolic summation. Two sequences are equivalent if and only if they agree from a certain point on. There might be poles in the beginning, there's some chunk in the beginning, but from a certain point on, everything is stable. And this forms, you get equivalence classes, and the equivalence classes form again a ring. It's just the same thing, and we use even the same notation. We write again sequence notation and say it's an equivalence class in our background, in our brain. Okay? And having that, actually we have now equality. Because this sequence equals that, because only one point is wrong. And indeed, this forms now a ring homomorphism. Okay. It's even an injective ring homomorphism. One can also show that. I want to skip this. This means it's an injective map. Okay? I will say more about that later. Okay. So we have now a formal ring, and we have given a evaluation function, and we can now have a correspondence between our formal ring and the ring of sequences. Finally, I have to introduce a shift operator. You have seen I solved the telescoping problem, so I need to shift objects. Otherwise, I cannot do symbolic summation. So I define, and a shift basically is a ring automorphism. You can shift in both directions. It must be bijective, and it should satisfy the ring homomorphism properties. You shift one object and the other, and you add first and then you shift. It should be the same output. Okay? And shifting a rational function, it's just you replace x by x plus 1. This is the ring or the shift operator acting on a rational function. You replace x by x plus 1. And similar, we can extend the shift operator if we consider this polynomial ring. And here we just have to see how the case harmonic numbers are shifted. If you take the case harmonic numbers and you shift them, then these are the case harmonic numbers plus one extra summand, which is 1 over k plus 1. Is that clear? So it's natural, if I want to shift my variable, it should be mapped to s plus 1 over x plus 1. And this tells me everything, just saying how this should be extended, because now by homomorphic extension, I just shift the coefficients by my previous definition, and s is shifted by s plus 1 over x plus 1. And this ring, together with the ring automorphism, is also called a difference ring. It's very simple. It's one of the simplest constructions. It's even simpler than a differential ring, where you need the Leibniz rule. This is a ring homomorphism or automorphism everybody knows. This is even more straightforward. And in addition, what we need later is the set of constants. These are all elements which are kept invariant with respect to the automorphism. Okay? And in our concrete example, the set of constants are just the rational numbers. So whenever you have an element from our ring, and sigma of the element equals the element, then the element cannot depend on h, on s, and it cannot depend on x. It must be a rational number. Okay? This is of course a strong property, and this is good to know. If you know the constants, and then you know a lot. Okay. And this is a special case of an r pi sigma ring. I will tell you later a bit more. Okay. So and now the important thing is the way how we did it, that the evaluation function and the shift operator, the sigma operator, and they interact nicely. We can combine the two operations. Namely, if you first shift s formally in our ring, and then you evaluate at the point k, this is the same as if you evaluate the variable at k plus 1. So the shift operator is naturally doing the shift operator. It's taking care of this. And this can be now, of course, connected to our tau, which goes from the ring element to the ring of sequences. If you take sigma of s, this is 1 plus 1 plus 1 half, 1 plus 1 half plus 1 third. But that's the same as shifting the sequence by introducing here in 0 and shifting it. And that's the same as the shift of, first you go to your sequence, to the ring of sequences, and then you apply the shift operator. So what we have done basically is that tau is not only an injective ring homomorphism, but it's an injective difference ring homomorphism. This means first shifting formally and then going to the ring world, sequence world, is the same as going first to the sequence world and then shifting the sequence. So the diagram commutes. This is so the automorphism sigma is catched in a nice way. Okay, and this means here we have our difference ring, or ring. Sorry, here's a bracket missing, and our automorphism. This is isomorphic because this is an injective difference ring homomorphism to the rational sequences joined with the case harmonic numbers. There's a one-to-one correspondence because this is just the image. Tau, the tau of this ring is this ring. And this is clear. There's a one-to-one correspondence because we have here bijection. And you cannot distinguish the two rings up to renaming of the objects. Because you can either shift here and then go to this ring, or you first shift here and then go to this ring. You don't see the difference. But of course in computer algebra it's a big difference if you work with sequences, which are somehow infinite objects, or if you work with variables. Here's a computer algebra word, here's the analysis word, which is a subring of the ring of sequences. And I utilize this property that there's a one-to-one correspondence between the two words. This is the input word, so if at least the combinatorialist gives me an object, he says it's a sequence, I represent it as an expression, but if you look in the paper, they always think as sequences. And they insert the sequence and then they want to get another out, but here I work with variables. And this is always a challenge in computer algebra, that you get something from the real world, you translate it in terms of variables, you do something and you go back. And if you do integration in Maple or Mathematica, all the bugs that are here are because the translation goes wrong. But here you have a one-to-one correspondence, and I did it so carefully that there's no bug. So this works. And I model it in the right way. So if I do something here, I know it's also the property is also here. And if the property is here, it's here. So I will not lose anything. That's the main feature. So now let's go back to our summation problem. We want to sum this case harmonic numbers. And we can state it in the analysis world, in the sequence world, given the sequence is 1, the case harmonic numbers, find another sequence within our summation domain, specified by the summation problem, such that this telescoping equation holds. And due to this isomorphism, this is equivalent to say, find a polynomial g in this polynomial ring, such that this difference equation holds. There's a one-to-one correspondence. Here, my algorithm actually runs in the variable world, and I find the polynomial xs minus x. And due to this isomorphism, I can immediately retranslate it to k times the case harmonic numbers minus k. And this isomorphism allows me to go backwards. And finally, I know it's j of a plus 1 minus j of 0. And doing the concrete evaluation, I'm here. So this is basically the algebraic framework, how it works. So let me give you now more details. What are the input classes, what I can do. So we start with a ring, and I always work with characteristic 0. So the rational numbers are contained in this ring. And these are the constants. So for instance, there was an n in summation variables which is not shifted. So this is a constant n. So it might be that it's, for instance, q of n. And I define automatically what is these are constants. This means they're automatically kept fixed. Okay. Now I join, for instance, the variable x, and I extend my automorphism, my constant automorphism, that x is mapped to x plus 1. You have seen this in the previous example. Then, for instance, I want to model k factorial. You have seen this also, the warm-up example. So if I shift k factorial, it's k plus 1 times k factorial. So it's naturally to take a new variable, and basically I also want to have 1 over k factorial in my input. So I go to the ring of Laurent polynomials. So I could say I just take a polynomial ring in P1, but I prefer also 1 over P1. It's more powerful as input. So I go to the Laurent polynomial ring, and I extend my automorphism by saying the shift of P1 is x plus 1 times P1. And in this way, if I do it carefully, the evaluation function, the corresponding evaluation function, and the shift operator commutes again nicely. More generally, it need not be the summand, the multiplicand need not be x plus 1. It can be an arbitrary element of my field below, except the 0 element. So any rational function being not 0, if I shift P1, it's A1 times P1. And this is nothing else than a hypergeometric product. So we call the sequence Hn is called hypergeometric if and only if there exists a rational function x such that how should I say, Hn plus 1 divided by Hn equals R of n. Okay. For instance, n factorial is hypergeometric because n plus 1 factorial divided by n factorial is n plus 1. I take x plus 1 is my rational function, and then it holds x plus 1 and many other things. Okay? And basically the A1 is precisely that. R equals A1. This is the witness of my multiplicand. Okay. And I can join a new variable, again a ring of the ring of Laurent polynomials, and I can extend the shift behavior by saying that the shift of P1 is A2 times P2, where A2 lives in the ring below, but it must be an invertible element. And saying that this is invertible actually means that it's an element of this type. So all C times P1 Z, the C is from K star, and Z is an integer. This would be the invertible element in our ring of Laurent polynomials. Okay? Nothing else is invertible. These are the units, the set of units, the group of units. Okay, and we can do this e times. So basically now, you see, in this way, I can define, for instance, products like that. this would be represent P1, and that would represent P2, for instance. Product within a product. Defining the corresponding evaluation function would give me such an object. Okay, and I can do this. So I have a product within a product within a product. You can do this several times, but of course this can be all hypergeometric. The A2 can depend only on Kx. This can be also hypergeometric, only hypergeometric products, but it can be nested. Another thing, what I have to introduce is, for instance, the alternating sign. This pops up very often in symbolic summation. And -1 to k has a property, if you square it, it's 1. So you have to introduce a new variable subject to the relation z squared equals to 1. And that causes problems because now you have 0 divisors. It's also clear. So if you have z plus 1 times z minus 1, this is non-zero in my ring because you cannot simplify it with z squared equals to 1. That's non-zero element, but that's 0 if you multiply out. This is z squared minus 1, which is 0. So you have a 0 divisors. Still, this is it. That's it. The world has to deal with -1 to n. In addition, if you shift z, it's minus z. Because this is, if you shift k, the alternating sign, you get -1 times -1 to k. Okay. And more generally, the inner guy can be a primitive lambda's root of unity. Then you have the property that z to lambda is equal to 1. Lambda is the minimal number, the order, and you have that if you shift it, it's gamma times z. And on top of that, you might introduce, for instance, the case harmonic numbers. We have seen already the shift behavior. This was our example. If we shift S1, it's S1 plus 1 over x plus 1. This was the example that you have seen earlier. But in general, the summand can be any element of our ring below. Any. It's a nested sum, because now we can introduce another variable. And the shift of S2 is S2 plus F2, where F2 lives now in our previous ring, which can also depend on S1. And I can do this again, as many times as I want. Okay? Even you can construct it infinitely if you want. A tower of infinite extensions, but in algorithmics, I stop from at a certain level. Okay. Now, this is just naive. Whenever I see a summation variable, a new variable, if I see an alternating sign, a new variable, and I join and I join and I join, this everybody can do. The important thing is, during this construction, is that the ring of the set of constants should not be extended. So when you take any element from this very general ring with all these variables, and it's constant, it's kept invariant, then it should not depend on any of the variables except the field k from which we started, which was per definition constant. So whenever you join new variables, never ever extend the constants. And if I can do that, then I have an algorithm. If you give me a summand, if I do the evaluation function, gives me the input summand, which I come from a summation problem, then I can decide algorithmically if there exists a G such that the telescoping equation holds. And if the constants are extended, then I don't know how to do it. Because the bound, the algorithmic idea is that I look at the polynomials and I make degree bounds. What is the highest degree in my polynomial? And if the constants are extended, then the degree bound can be arbitrarily high. And I cannot bound it anymore. And I cannot say how high should it be, and then I can check if there's a solution in this restricted domain, but I will utterly fail. But if the constants are not extended, there's a bound, and there's only one bound, and it cannot be higher. So I have algorithms. But if the constants are extended, game is over for me, and I don't know how to do it. Okay. Let me show you how this can be done, that the constants are not extended. Let me give you some more details. So let's start to represent sums. So let A sigma be an arbitrary difference ring on this level. So I have constructed already several sums below, and everything is nice. And let's take the set of constants. Okay? then in general, because I start with a ring, the set of constants is a ring. One can easily see it. If you take two constants and you add them, you get again a constant. And if you multiply a constant with a constant, it's again a constant. You stay closed under the property. It's a ring. In particular, the rational numbers are included because 1 must be always mapped to 1. It's a ring automorphism. But then 2 is mapped to 2 because 2 is 1 plus 1. And by the ring homomorphism, 2 is mapped to 2. So all integers are mapped to itself. But then the quotients of the integers must be kept fixed also. So there's no way out, the rational numbers are fixed. With the complex numbers, it's different. The imaginary part can be mapped to minus the imaginary part. Different story, but the rational numbers are kept fixed. And in my constructions, I always start with a field, and I take care that they always stay in the field. So the constants will be always a field. Okay? I can handle this. I start with a field, and when I join new variables and I never extend the constants, I will always have a field. So let's suppose now that we are given a difference ring with a constant field. So the set of constants forms a field. Okay? Now we do the naive game. We join a new variable, so we go to the polynomial ring, and I extend the shift operator. The shift of t is t plus the summit, where f lives in my below. This would be the naive construction. And now the main goal is don't extend the constants. And there's a following theory. It was originally introduced by Michael Karr in the field setting, and I generalized his result for an arbitrary ring. Before it was Michael Karr did this for the field version, and because I work with rings with root of unities or something, I generalized it for the rings, and you have the following statement. My original ring is a constants, and the extended ring has exactly the same constants, so I don't extend the constants, if and only if there does not exist a g in my ring below, such that this difference equation holds. And such a difference ring extension, so we extended the ring and we extended the ring automorphism accordingly, is called a sigma extension. So here I follow the terminology of Michael Karr. He called it sigma extension. Okay? And this has now a nice feature. There are two cases. There does not exist a g such that this difference equation holds. Then I know it's a sigma extension. And the constants are not extended. So if I fail to find a g, then I can do the extension. If I find a g, this is shift behavior, there's no need to introduce a sigma extension, because you see, I introduce a new variable to model this shift behavior. But here I find in the ring below already the shift behavior. So why should I introduce a new variable if I have already the property? Okay? So if you have a polynomial with coefficients in a certain field and you want to have a root, and the root is already in the field of the coefficients, you don't say root of, you take the element from your field. Only if the field does not provide a root, then you say, let's introduce a new variable, and then say root of this polynomial to deal algebraically to introduce a new root. So this is the same idea. So basically this is a nice feature. And I'm closed. Because in particular, I have an algorithm to check if there exists a G or not. If my ring is already constructed nicely, and I have a new sum, I can check, does there exist a G or not? If there exists a G, I just represent my sum that I see by this G. It's like the telescoping in the Warmup example. And if I don't find a G, the algorithm tells me it's a proof, there is not a G. Then I can join a new variable, and I'm safe. And I can lift from the simplest case and go upwards. I can do the construction. Okay. So solving the telescoping problem and doing the right construction is a one-to-one problem. It helps. One cannot live without the other one in order to do the construction. Now let's go to the product case. So let again A sigma be a difference ring with a constant field. We do again the naive construction. we join a new variable because we see a product, so I go to the Leroy polynomial ring, and I extend the shift operator. The shift of t is a times t, where a is a unit, an invertible element. And then there's the following statement. The constants are not extended if and only if there does not exist a g, and there does not exist an integer, but not 0, such that sigma g equals a to n times g. This is somehow the multiplicative version of the previous one. And here, well, you don't see the n, but if you would formulate it, yeah, you could sneak in an n in addition. There does not exist a g, and there does not exist an n being non-zero, such that this holds, and the multiplicative version would be sigma g equals here we should write f, and the multiplicative version would be g times f to n. This is then the corresponding multiplicative version. Plus and minus goes to times division, and times goes to the power. Okay? The proofs are completely different. There's no proof for both in the same thing. You have to do different, but the zero theory somehow is similar. And such a difference ring extension is called a pi extension, where the constants are not extended or where you have this property. It's an equivalent. And now we have three cases. Well, there does not exist a g, there does not exist an n, except the 0. The 0 would always be possible, such that this holds, and then it's a pi extension. Fine, we did the right construction. The other thing is there exists a g, non-zero, such that this holds, where n is equal to 1. Super. I found the right shift behavior already in my ring below. I would be like in the sum case. But there's a third case. There exists a g with this property, but not for n equals 0 or 1. For instance, n equals 2 would be the smallest choice to find such a g. And then, game over. I cannot model on my object anymore. Now, of course, I could take an idea. I can factor out this relation, but I don't want this. I don't want to work with ideas. So, here are several scenarios. Let's look, for instance, at the hypergeometric case. So this is again our simplest case. We consider our differencing that you have seen also in the examples. Shift of x is x plus 1, and k is a constant field. Take arbitrary multiplicants. And they know this is hypergeometric multiplicants. Then there is a difference ring E with exactly the property, namely for I find G1, G2 up to GR such that this shift behavior holds. So I can model all my products in this ring. Let me show you how this ring looks like. It's a tower of pi extensions. Like I join new variables, and I can introduce the shift behavior accordingly, plus one root of unity extension. So I take a root of unity such that set of lambda is equal to 1. It's a lambda's primitive root of unity. So I have a tower of pi extensions plus one special R extension. You have seen this already earlier in here. This was this line where I had this root of unity. And basically the lambda is basically the minimal n. So I have to raise it to n to 5, for instance. Then with high probability I need a 5/5 root of unity in order to catch it. But this root of unity allows me basically to make somehow a trick that I get rid, introducing this root of unity, I get rid of this n and I can somehow set it again to n equals 1. So the root of unity is a troublemaker, at least for the hypergeometric case, why I enter in the third case. Okay, and let me say there are also results for the Q rational case, where Q is not a root of unity. Alex, I have seen a paper where you do this root of unities products or something. This I exclude here. So it should be a variable Q. And I think one can do it also for 2 or 3. I haven't done it carefully, but this is the word how I can do it. And also the multi-basic case, I have Q1, Q2, Q3, or so on. And also the mixed case, where I have X and I have the Q versions. So Q1 to K. Also, maybe I should say this, the Q version would be intuitively such a ring. That would be the Q version, where I sneak in also Q1 to N, QE to N. This also works in this scenario. So basically the Q hypergeometric world, the hypergeometric world, and the mixed hypergeometric world, this can be all done nicely. And there's room of improvement to think of more. My colleague, a PhD student of mine, has done now this for nested products, what I showed you, that you can always reformulate nested products in such a setting. Okay, so summarizing, if you give me an arbitrary expression in terms of hypergeometric products and sums on top of it, I can always step by step construct such a difference ring in terms of variables such that the constants are not extended. And therefore I can solve the telescoping problem. Okay, so now you have seen in the beginning sigma reduce. I applied sigma reduce. So I had an input expression in nested product sum expression, and the output was a nested product sum expression. And well, the property is A equals B. Input expression should evaluate to the same as the output expression. Otherwise it would not be a simplification from a certain point on. But more can be said. Namely, the arising sums and products in BK are algebraically independent. They don't satisfy any relations as a sequence. And I would like to justify this a bit. And here now comes in another aspect of difference ring theory, namely a kind of Galois theory. Let's look again at our naive construction, joining just variables without taking care of constants. So let's look at this ring I've just naively constructed. Then I showed the following result of equivalences. Namely, the following statements are equivalent. The constants are not extended is equivalent to say that the ring that I obtained is simple. This means if you look at all ideals in A which are closed under sigma, difference ideal, there are only 2 cases of a difference ideal. Either it's a 0 ideal or it's a full ring. There's nothing in between. This is equivalent to say the constants are not extended. Third statement, there's an embedding from our ring, or formal ring, into the ring of sequences. We have seen this here. I just looked at the very simplest case, QXS. And I said there is an injective difference ring homomorphism. I could embed my formal ring into the ring of sequences. And this holds in general. If I have a difference ring, naively joining variables, and I took care that the constants are not extended, give me any difference ring homomorphism into the ring of sequences, then I know it must be injective. Any. If it's a difference ring homomorphism, it must be injective if and only if the constants are not extended. It's a very strong statement. So I only have to take care that the constants are not extended and my eval is doing properly the job, then I know automatically it's injective. And there's another statement which I didn't use too much so far, but there might be interesting algorithms. There are idempotent elements E1 up to E lambda, such that E can be written as a direct sum, and the E1 up to E lambda are integrate domains. These are, again, these rings with variables where the root of unity guy is gone. I have, again, integrate domains. And for instance, if I look at x squared equals to 1, I have 2 idempotent elements. One is 1 minus x divided by 2, and the other one is 1 plus x divided by 2. Okay? And the sequences would be 1, 0, 1, 0. And I think the other one 0, -1. And maybe up to a minus sign, but something like this. So we have these two idempotent elements, multiplying them by other mark product, you get 0, multiplying it by itself, you get the identity. So you can factorize this, and this is an integral domain. This would be a pi sigma extension in the Karr sense. Another aspect. But here I focus mainly on part 3. This is for me the most important in the moment.
So how do you define P sigma extension?
In this setting, a pi sigma extension is that without this. I don't allow such a root of unity extension. Just what you get, E1, E2, it's a copy of that, where the shift is actually sigma of lambda somehow, and this is removed. And then I have just raw polynomials in polynomials extensions. There is not anymore a zero divisor in these rings. So pulling out the idempotent elements allows you to work. So it's basically kind of interlacing. So I can work with -1 to n, or I can work with that sequence and that one. If you take a linear combination of the two things, then you can always write f as E0, F0 plus E1, F1, and you can do it by polynomial remaindering. You get an F0 and an F2, F1, and F0 and F1 is free of x by taking polynomial division. You divide by x minus 1 or x plus 1.
Could you show that slide again with the equivalence?
Yeah. So if you shift an element, you shift once, and you basically have this copy. This would be the first entry. If you shift once, second, you get the second entry of your sequence. If you shift several, next time, you come to the next entry of your sequence. And if you're here and you shift once more, you are gaining this copy. So it's a kind of interlacing. You have, maybe if you have a fifth root of unity, then you have 5 copies, and you shift. And then if you go the 5th time, you are basically like in the beginning, where you just shift this once, but 5 times. And the -1 to n is gone. You can work in such a way. And let me say, similar results have been also worked in the Galois theory of difference equations. So there's such a statement of similar kind, but he is more general in some sense, and then he has to go to the algebraic closure, and this complex numbers must be contained. So this can be world functions. If you have q of n, and then you go to the algebraic closure, then I don't want to see this in computer algebra. But here, I don't need this. I just work with constants which I'm starting with. I have full control of this, and I don't have to go to these very fancy constructions. I'm down to earth here, and it works. In some sense, this is a specialized case because I have only first order difference equations, but they're nested. In particular, the products are nested, and I'm falling out of the standard Galois theory of difference equations. So in some sense, I'm restricted. In some sense, I'm generalized. One cannot say it's more general, and one cannot say it's more restricted. There's an intersection in applications, very strong intersection, and then it goes in different directions. And it works also for the Q-rational case and the multi-basic case, the same thing. This is done in one stroke for all. Okay, now let's go back to the situation. I start with my summation problem. I construct the corresponding, I represent my summation problem in this difference ring, cleverly by taking care that the constants are not extended, using the structural results. Then I find an element, so in other words, I find an element in my ring together with an embedding such that applying my embedding to A, I get my input sequence. So I modeled the thing in the right way. So you have seen this here. I have done my embedding and I have a one-to-one correspondence. And applying tau of S1, I come here to the corresponding thing in the right way. Okay. And reinterpret, now what sigma reduce is doing, now I take this A in my formal ring and I reinterpret the variables by the evaluations and say, okay, x is my rational function, s corresponds to the case harmonic numbers, so the evaluation gives me the expression how I represent the object, and this is the output of sigma. And the statement now is, here I have the rational sequences, here I have the root of unity guy. And the interesting thing is, because it's an embedding, the variables P1, P1 minus 1, this is a Laurent extension, but also the sequences are algebraically independent because it's an embedding. If I have a relation between these two sequences, I would have a relation between P1 and P minus 1. So these are nested products, and these are nested sums, and they are all algebraically independent in the algebra sense. They form a Laurent polynomial ring extension, and on top they form a polynomial ring extension. And there are no relations among these variables except the case that P1 times P1 minus 1 equals to 1, the trivial. But otherwise they are algebraically independent. And this justifies now to say, by Galois theory, output that I deliver, the products and sums are all algebraically independent.
When you say algebraically independent over the which field? Or?
Over this, actually over this field, but then also adjoint to that ring. So it's basically algebraically independent over a ring, which means there's no polynomial relation. But yeah, if you say algebraic independence, it's always a debate, must it be over a field or can it be also a ring, the coefficients? So I say a ring is also fine. Okay. In application 1, well, the expression B normally is much simpler. And application 2 is we solve the zero recognition problem. Namely, A evaluates to 0 the input expression if and only if the output is 0. Because I model it in my ring in a one-to-one correspondence, and in the ring I have the 0 element if and only if it's a 0 element. It cannot be something else. Okay, let me show you quickly some 5 more minutes. Is it fine? Some examples. So all these tools that I've shown you, all the theory, is used to evaluate Feynman integrals. So I'm not a physicist, I cannot say too much, but this is a typical Feynman diagram, and it's a visualization of the process. So you have here, a particle goes in, a certain behavior of certain probabilities, some interaction, and then the momenta gets out again. And if you have a physical problem, you have thousands of such integrals, and you have all to add them up to get the behavior with probabilities. And the nice thing is, this is a graphical visualization, and the physicist can immediately say what are the actions going on, and there's a translation to a Feynman integral. There's a direct translation. This is not difficult. And the difficulty now is, this is now a mathematical object in some sense, and it's very, very hard to evaluate it. It's very difficult. And let me just show you a simple example. Actually, this is very simple. If you want to integrate x from 0 to 1, we know all what it is. X squared, we also know what we get. X to 3, we also know. And more generally, x to n, we know. And such an n pops up very often in our calculations. This comes from operation insertions, and we get such discrete parameters in addition for Feynman integrals. I cannot say you too much, but this is a Mellin variable, and it's a discrete parameter which pops up in Feynman integrals. And somehow this is a first Feynman integral, but it's a bit more complicated. So we have something like that, and Feynman integrals normally are not properly defined in the mathematical sense because they are divergent in space-time form, 3+1. So in physics, what they do is they introduce a new small parameter and they go to 4 plus epsilon. This is a kind of analytic continuation of the space-time. Okay, I cannot understand what this means, but it's a good trick how they can handle it. And then they basically are interested in the asymptotic expansions. They look at the Laurent formula expansion, and if you do a 3-loop calculations, they know it starts at epsilon minus 3, the first coefficient, and they're interested in the first 3 or 4 coefficients. This tells them this is a divergent part, and this helps them to control the whole thing. So they have this epsilon parameter, but it's still more complicated. It's maybe a 6-fold sum integral, and there are other discrete parameters involved where you sum over it, and then you have such an integral. And it's very difficult. Actually, there are tools also from integration, symbolic integration. So a multivariate Algorithmic algorithm would fit into the input class because it's hyper-exponential. But our tools fail utterly. So what we did is we translated that sum with my colleague Johannes from DESI, Deutsches Elektronensynchrotron. This is a big institute in Hamburg, and in Berlin, it's in Germany, a center for colliders. And they're also it's one of the big project partners at DESI, at the Large Hadron Collider. And we can translate this to complicated multisums by Mellin-Barnes techniques and hypergeometric tools. You can translate. And if you do it stupid, you get even a worse output. If you do it good and clever, you get a similar complicated expression. So to get something simpler happens very rarely. But still, working with discrete objects is sometimes better than with continuous objects, because you can much more control things. In particular, we have our strong tools, in particular the summation theory. And you have seen the first warm-up example in the introduction. This was a simple case, 2-loop example. You have seen the tools in action. Let me show you another example. This is the example that I've shown you. This beginning, this complicated integral. And you can look at its Laurent expansion with respect to epsilon. As I said, they are divergent, space-time 4. So they look at the Laurent expansion, and they are mainly interested in the constant term. And translating this integral to a sum representation gives you that. It's again a 6-fold sum, complicated, and the harmonic numbers. It's somehow similar to the warm-up example, but more complicated. And in about 1.5 days, calculation, automatic processing, you get that expression. Well, the output is bigger than the input, but now these are all special functions. You see here the harmonic numbers of second kind, and this is the most complicated object. It's a 3-nested sum, the harmonic numbers, then we sum again, and we have here the alternating sign, the -2, 1, 1 encodes this nested sum. And we have asymptotic expansions, we again know everything about it. Let me show you, yeah? No, okay. Let me show you a last example. This was last year. This was now more advanced. It's a 2-mass 3-loop Feynman integral, so we have 2 masses inside that we have to deal with in the integral. And doing Mellin-Barnes and PFQ techniques, I got an expression of 100 megabytes of 150 single sums, 1,000 double sums, 12,000 triple sums, and 1,500 quadruple sums. Okay? One triple sum looks like that. It looks like the warm-up example. And it took about 6 hours to do the sums. So if you do estimates, it would take maybe 10 years with strong computers to do all the expressions. But I didn't do it. We do it differently. I merged them in a very efficient way. And I had to look only for 8 sums. But it blows up the summons because I have to do synchronizations. And do synchronizations and mapping it to one summon blows up things. And now I apply a valid multisum, all the toolboxes, to simplify, to go from inside to outside. And let me show, for instance, a quadruple sum. This was a summit of 266 megabytes. So this is not anymore a warm-up example, Alexei, because it's now bigger. And in about 2 days, I simplified it, and I got indefinite nested sums in about 1,000 sums. And here's a quadruple sum. The summit was 1.6 gigabyte. And it takes about 11 days. It took about 11 days, and I found about 800 sums to represent. So doing all these 8 sums took about 3 months on several computers, and it was an expression of 154 megabytes consisting of 4,000 sums. But of course, these were independent calculations, and there were relations among the sums. Now I apply all these techniques, eliminating all algebraic relations, and in about 1 month, so one of these sums is, for instance, this was one of the most complicated sums. This are again indefinite nested sums. K goes from 1 to j doesn't appear inside, j goes from 1 to I doesn't appear inside, so it's indefinite nested. This eta is a quotient of the 2 masses of the Feynman integral, and we have here the central binomial coefficient. So it's a 1, 2, 3, 4, 5, 6 nested sum in some sense. And in about 32 days, eliminating all algebraic relations using Galois theory to justify this, I get an expression of 8 megabytes of 74 sums, and it fits on 2 pages. And precisely these outputs are now in special function form that are useful, and it's processable by physics, and sooner or later, we are soon there with all our calculations. They will be used at the Large Hadron Collider at CERN to predict the coupling constant in a better way, for instance. And this is, for instance, interesting because the forces of the universe, if you look at the current calculations, they look like they have one common origin, but the curves do not meet in one point. And the problem is there's a 3% error in the theory that we have in the moment, and we would reduce it to below 1% error. And it's interesting then to see if the curves come closer or go further away. If they get closer, it's a hint that there's a common origin of all the universe forces, but if it goes away, it's just a coincidence. But this will be one of the interesting results that we try to get out. And with this, I would like to finish my talk.
Any additional questions?
In your original post problem, you have a double summation to infinity.
Yeah.
What if the upper limits are not infinity, but two finite numbers?
This was, for instance, here, this example here.
Yeah.
Or you have seen here, and you have seen also the second example of the Warmup example. Let me.
So the method works with finite summations.
So you see, for instance, I compute a recurrence, and here I would get now a truncated version.
Right.
And I could now plug in a equals n. Then I have the finite version. If I want the infinite version, I have to perform now the limit.
Right.
So it works for the truncated versions or for infinite versions.
And now if you were trying to numerically compute these things, what's the difference in efficiency by using the summed version and the original definition?
So I don't know how to do evaluations here. So to do fine evaluations, I don't know how.
I mean, the parameters in your summation.
I mean, there are tools, at least in particle physics, there are tools if you get a Feynman integral, there are tools to do numerics to a certain level, and you can do it up to a certain level. What we want to do is the analytic result, because the physics guys want to know what are the functions behind which describe the universe. These are the atomics.
Yeah.
Also, you see they compose previous calculations with new calculations, and they are already analytic there.
Right.
Now, if you find the other calculation and you want to match it, then there's an overlapping, and you see the functions match, then this is an indication that it's a right calculation. So you have many checks. If you have numerics, you have no control, you just add numerics, and you have to trust that it's correct.
No, my question is, in doing the numerical computation, does using the summed formula faster than using...
Of course, if you have special functions in indefinite nested form, there are very efficient ways to do numerics. And you have better control. You know, I want to go to 1,000 digits, and you can do it very efficiently. Of course, there are constants which converge very slowly. I agree.
Right.
But there are very few. Maybe normally you have physics calculations. There may be theta 2, theta 3 Catalan numbers, and other things, and you know how to calculate them, or you have them up to a certain precision, and you use these precisions, and you don't have to redo it all the time. But we obtained several new constants, and then, of course, if it's the first time that we see these constants, we had to do it, and sometimes we had problems to deal with it. But we have some representations or integral representations in indefinite nested versions, and we could work with them with our available tools to get it.
What about exact computations?
I mean, what we are doing is exact, if we are in the symbolic form.
No, I don't mean that. I mean, when the parameters are known,
Yeah.
and you want to evaluate these sums
Mm-hmm.
exactly for finite sums.
Yeah, I do this. So for instance, I mean, if you have a limit involved, then the limit is always somewhere where you have something hidden. But if you look at that sum, if you plug in n equals 5 here, and plug in n equals 5 here, you get the same value. If you plug in n equals 100 here,
No, I don't doubt that.
Yeah.
I don't doubt the
this is exact.
correctness.
So what do you mean is exact?
Rational number coming out with a rational number.
So if you plug in here a rational number, you mean?
Yeah, I mean they are rational numbers, right?
So how to interpret this? I mean, this is another interesting thing. In physics, they start normally, how should I say? They start with an object where n is indeed a rational function. And then we interpret it as an integer. Then we do the whole calculations on the integer level, and we know input, output on the integer level is the same.
Right.
And then we use something like the Carsten theorem. If we have functions which do not oscillate too much, and they have only asymptotic behavior like e to x, exponential growth, then you know if the two functions agree on the integers, then they have to agree on the complex plane in the analytic continuation.
Right.
And therefore, we can do an analytic continuation on this level, because here we know it's related to the gamma functions, and then we know it's also the analytic continuation of this object. But doing the analytic continuation here with upper bounds for sums, for me this must be discrete. I have a big problem. So here I'm already in the middle of a calculation where I'm already on the integer level. But in a previous calculation, the n is still rational or complex. But here I'm already on the path of being integer, but on this level I can reinterpret it now as a complex object, and I know my original input will behave the same by the analytic continuation. But here already there was a previous thing where I have a Mellin transform, something like that. And here n still can be complex.
Okay.
But then I go to the sum representation, and then I stick to integers.
Right.
I do now all the integer level, and I can do dirty checks, things which I can normally you can always link to the previous thing, but here game over, or I don't know. But in the end I get the result, and by Carsten's theorem I know if I do an analytic continuation here, it must be the same behavior like here. I was also not aware of the Carsten theorem. In physics I knew it, and when I saw it the first time I was extremely happy, because also in symbolic summation we do it at other levels, and then it was always hand waving to say it holds. But this theorem is very strong from the 20s.
Is this theory limited to one single variable?
No, there can be also more variables involved.
Can be.
So you have seen also the massive case. So where we have an gamma, eta involved, the quotient of two masses in the end. But the more variables pop up, the harder it will be. To get a recurrence is still fine, but the more parameters are involved, the more likely it will be that I cannot solve the recurrence.
Right.
And in particle physics, very often they give me some representation and they say game over. But then they say, let's do it differently. They have a better way to do it. The output doesn't look too much different from the size, or it gets even worse. But suddenly it gets through, because they did a transformation before, which was made it simpler, the expression, but it destroyed the structure to do summation, and avoiding some transformations, PFQ level or something, suddenly it went through. So this is art. And having several variables makes it more complicated, and the more art it is that the machinery still works. And finally, in the last years, we had also calculations where we get out of the class of functions and the elliptic functions, for instance, pop up or something like that, because we are more and more entering more complicated calculations. And well, if we leave the world, then of course it doesn't work. But it's stupid if we leave the world because stupid manipulations introduced it.
Anybody else questions? May I ask a nonsensical question, perhaps? How strong is the relationship between, let's say, for one variable, a recurrence relation and a summation?
So, in all examples that in physics...
So maybe I put it the other way. Finding the sum of an expression, summation sum, and solving the recurrent relation, aren't they really just related? They're the same thing, or they're not?
Well, if you look at that sum and you get this recurrence, you see this is a definite sum, or at least the limit of a definite sum, whereas the output here are indefinite sums. So my trick is I translate it to a recurrence, and then we have stupid algorithms which only find indefinite nested sums.
Okay.
And then, of course, if I find sufficiently many solutions, I find an alternative representation which is better, in my sense, because it's only, by default, the recurrence of our finds only indefinite nested sums, but the input might be definite.
Right.
So I have a simplification of the same sequence. On the sequence level, it's the same, I agree. But the representation of the sequence, or the algorithm to calculate the sequence, is a different one. This is very hard to calculate n equals 2, 3, 4, 5, 6. Whereas here, it's very efficient to calculate n. So it's a better algorithm to calculate the same sequence. But it's also a weakness because I find only indefinite nested sums, and it would be beautiful to have a recurrence and to find definite solutions. This is a dream, but it's unsolved. Marco Petkovic has a solver for certain cases.
But in terms of, I know, in terms of computation, yes. Okay, and so you can compute directly, find a sum, or you can compute a sequence using recursion. But I like to know abstractly.
Oh, okay. So for instance, we calculated, we had recurrences, and by guessing, we found recurrences of order 40.
Right.
It's 200 megabyte size. So it's order 40, the recurrence, and the degree of the polynomial was 5,000. So, and the irrational coefficients the integer coefficients filled one page. So it was maybe 10,000 digits. So it's a gigantic recurrence. And then we solved the recurrence, combined the solutions, and the output was two pages. And this was a minimal recurrence by guessing.
Right.
We know it's very likely the minimal recurrence. So sometimes the representation in this closed form is better. In particular, if you have it already in harmonic numbers, then asymptotic expansion is easy. If you have a recurrence, you can also get asymptotic expansions up to constants. And they're very hard to get.